Okay, so now it's recording. So this will go onto YouTube and like be for people to review. So for the first one, we're just talking about the same way you guys have been doing anti-Markovnikov addition across the double bond, and then basically it's being oxidized all the way down to an aldehyde. And so that's something that's just a reaction you guys need to know. This is just the good old classic way of using alkynes and eliminating them, eliminating this hydrogen here. And those electrons can work as a nucleophile to attack another halogenoalkane. Then we've also got just acid and water right here. So this is going to add Markovnikov style, and then it's actually, because you've got also the mercuration component, it's going to take it all the way down to a ketone. So that's just something you need to know. That's something from Orgo 1 that hopefully you carried over. Then we've got Linlar, and you've also got sodium salt with liquid nitrogen. And so I'm going to compare this with something else in a second. But first of all, I just want to talk about Linlar for a second. So Linlar is a great reducing agent because it consistently creates cis configurations. And so we talk about cis and trans, and those follow just the Kahn-Engel-Prelog rules. So if you remember back when we did assigning stereochemistry and we were assigning stuff 1, 2, 3, and 4, the highest priority is kind of what matters when you're looking at cis and trans. So the highest priority needs to be on the same side of the double bond in a cis molecule. And then in a trans molecule, the highest priority is actually, they're opposing. So they're on opposite sides of the double bond. So one will be down and then the other one's going up. And yeah, that like that. That looked terrible. That didn't help. But just know that it adds cis and it only reduces one. This one right here, based on this number of sodium equivalents, is the number of hydrogens you're going to add. So like for this one, we added 2 hydrogens. So we used 2 equivalents of sodium. And I'm going to go a quick little tangent here and talk about this bad boy, which is a nice cousin of this bad boy. And so basically what I'm going to talk about is this one, when this leaves, has got a negative charge. So it's a base. It's a strong base. And this base is actually going to be what you use when you're doing your reactions where you're taking stuff off here. And so it's a eliminating like reagent. The difference is with this bad boy, where you've got 2 sodium and then you've got liquid ammonium, is that it's actually going to add protons. So you've just got one where there is a lot of basicity. So there's a lot of stuff that's like trying to take away hydrogens. And then you've got this right here, which is just like a salt that's going to stabilize this guy, giving away his hydrogens. So I know it kind of looks similar, but the difference is that this one is already in this state. That one is missing hydrogens and is actually looking to gain hydrogens, whereas this guy is willing to give away his hydrogens. Does that make sense? And it's important to remember that one's trans, so this adds trans. Moving on, we just did acid and water here. This is just regular Markovnikov. It's going to allow you to do shifts. It's not concerted. Next, we've got, I think it's hydroboration. I think I said that right. And it's just anti-Markovnikov alcohol addition. So do you guys have any questions there so far? No? Good. Moving on down, we got oxymercuration, which is just going to add like a concerted Markovnikov alcohol. Then we've got osmium tetraoxide, which is going to add syn-diols. So across a double bond, it's going to add alcohols on both sides of the plane. And that's important. This should be connected here, sorry. Excuse me, because later down in here, this is a reaction that you're just going to need to remember. And it doesn't really something that we talk about too much, but it's usually on the ACS, and it's a free point if you remember it. And remember, ACS points are going to bump your grade up more so than anything else. So remembering that is going to help you. And I connect those two because you can use a double bond and then go to here and then go from here to add this guy, and it's going to actually split them. And I'll talk about that more in just a second. So more of what we're doing in Orgo 2 is you've got to start to become comfortable with this like annealing basically cyclic structures back together. So you've got like strings, and you start to get comfortable like counting out your carbons and then realizing like, okay, there's 6 carbons here, and on either side of the 6 carbons, there is a ketone. That means that there was probably a cutting that happened somewhere in the middle. And that just is something that becomes more comfortable. So that's, yeah. Somebody said something in the chat. Then, okay, so this is a good, this one is in your OWLs, and it's on the ACS, but it's not one we usually talk about much. It's important to remember. So I think of the NBS as standing for next, and then think of the N. Whenever you see N, just think of next or like beside, and then the S is just like, I don't know, supporting, or I don't know, man. All that you need to remember about this reagent is that it's very unique because it adds a BR, not actually to a double bond, but it adds it to the allylic. So it adds it to 1 over. And so as we talk about conjugation, you'll start to understand that better. But basically, it adds not to the double bond, it adds 1 over. And yeah. Does that make sense? Yeah. Because basically electrons here can go over and stabilize this. So like this carbon right here is more stable than like if it were a tertiary. Does that make sense? But usually we just use it to add just next to a double bond. And that's all you really have to remember for it. Peroxides and hydrobromic acid, you're just going to add anti-Markovnikov halogen. This right here is going to flip. These two guys do the same. I still don't really know how they're different. All they do is they flip the stereochemistry, and they make it either a Br or a chlorine. And yeah, so this goes from like R to S or S to R, and that's about all. Next, we're going to talk about oxidation agents. So you've got dichromic acid, you've got chromic acid, and then you've also got like chromate or whatever, PCC. And they're all these different things that are going to take stuff from alcohols down to either carboxylic acids or ketones. And it's important that you know what's going to take it to an alcohol to a ketone or an aldehyde, I mean, versus what's going to take it to carboxylic acid. And that's kind of why I avoid dichromate and just only use these two, because they're surefire. You know when you're using chromic acid that it's going to oxidize it as far as it possibly can go. And you know when you use PCC that it's only going to take alcohols and make them into carbonyls. So that's kind of the gist of it there. This is like what I was talking about, something that often is used in combination with osmium tetraoxide. And really what it does is it just splits this bond and then ultimately creates a planar little section there. It looks sort of like ozonylysis product. Yeah, any questions so far? Okay, and then the next we've got basically a Grignard that's reacting with an epoxide. And so I went ahead and drew out your arrows here, and I drew them all at the same time. So everything is happening at once. But in reality, you know, you've got your Grignard that's going to attack the epoxide. And you can really think of epoxides as just this component here. When you see this right here, where you've got 2 carbons and then a terminal alcohol, think of an epoxide, because that's where you're going to be using Grignards to create those. And yeah, it's important to remember that this was originally like a negative charge, but then once you do the acid workup, it becomes an alcohol. Any questions on that? That's usually on the ACS. This is another thing similar to this one. Woo, that was wild. Sorry. This right here is similar to this one in that we don't really talk about it too much, but it's usually on the ACS. So this just adds almost like an epoxide, but it's like 2 things that pucker together and it connects to a single carbon. It's really weird. So when you see this, just remember that you've got like, whenever you see zinc and copper with the 2 iodines, those 2 iodines are eventually going to become bonds like to the carbon. Those 2 bonds that were to iodine become bonds to like the carbon structure, if that makes sense. And that's all there is to say on that. Just remember it. This next one looks complicated at first. It's really not. It's not scary. This potassium is supposed to dissociate, and it leaves this cyanide ion. And cyanide's great because there's a lot of stuff we can do with it. You can add just water to it, and it'll become like an amide, which is crazy, and fun stuff like that. Anyway, not stuff you need to know for right now is the amide. The amide stuff isn't stuff you need to know right now. But hopefully you're comfortable with, drawing that nucleophilic attack to the electrophilic site. And then, that carbonyl group is going to become like an alcohol at the end there. So yeah, this next one, you don't really need to worry about like steric hindrance for this one in particular. When you're using these metals, don't think about steric hindrance as something that's a problem. This is literally like a circle that's a punching into a nucleophilic or electrophilic site on a carbonyl. And yeah, so that's that. Not too much more to say there. Do you guys have any questions there? Cool. This is a Wittig. Wittig, like I've been saying, is no need to overcomplicate it. Whatever you've got here, you can just replace the oxygen with whatever's there. Remember, the positive side is on the phosphonium ion. The negative side is on the alkane or the methyl or whatever it is that you're using. Protection is really important. You've just used these little diols, and they make nice little protection groups that when you drop water on there, go right back away. So actually, I screwed up here because as soon as you add acid, it makes it disappear. So it goes straight back down to there when you add the acid. Wait, let me fact check that. I'll get back to you on that one. I'm not sure that's right. I need to talk about that or look into that. These, you don't need to overcomplicate. Think of the hydrogens as just becoming bonds with the actual main carbon. So however many hydrogens there are, that's how many like bonds to the carbon there's going to be. And really, that's how I differentiate between whether something's going to be an imine or an imine, enamine or an imine. I think that's how you say it. But remember that you have to add this weird double bond after like the fact of the bond to nitrogen. Does that make sense? Cool. Are there any questions here? I went really slow. I'm going to pick it up a lot. Okay, so this next section, you've got a ketoaldehyde. So I'm going to work this whole like thing like in retrosynthesis style. And then I'll actually do the other presentation like in office hours. So I'll let you guys have the full time for your thing and all that for your break rooms. Sorry. So we're starting out here with this molecule. We see this molecule and we see that we've done some type of oxidation here. That's an oxidizing agent. And we see that there was a ketoaldehyde. So that means that considering this is a carboxylic acid, and this is a ketoaldehyde, what probably happened was that aldehyde turned to a carboxylic acid. And that's what this oxidizing agent here did. So that's the first ketoaldehyde. And then once you've done that, you can mark off and number off all your carbons. So like I was saying earlier, you're going to want to start numbering your carbons. And when you see two carbonyl groups that are 6 or 5 carbons apart, think about how those might have been come from, like, you know, a ring originally that broke apart. Or maybe they could go back and become a ring. Maybe that's where we're going. And so when you're doing that, it's important that you like label off the substituents for each carbon, because being able to do that bookkeeping from line to circle is big. Can the pi bond be next to the other methyl group too? Yes. So exactly, that molecule is symmetrical here. So yeah, and that's where I'm going. So once this right here is done, it's osmium tetraoxide. It is actually from this is where you figure out like that product was. And then that could be either side. You're adding heat and water, or you're just adding heat and acid. And so you can look here and see that that was an alkene. You can look right here and see that, okay, there was once an alcohol there, based on how there are 16 hydrogens and 8 oxygens. That means there's 2 hydrogens for every carbon, or 8 carbons. I hope I said that right. So that was an alcohol that got eliminated to form this bad boy. After that, we've got the ketone here, which was formed from the reduction, or actually this alcohol was formed from a reduction of a ketone based on how we use Wittig with it, and then also just the number of carbons and hydrogens in there. You know, it's a ketone. And so from there, the very last step is just to add Wittig, and Wittig is just going to substitute out your oxygen for your carbon. Any questions? And that's all. Alrighty. Yeah, it is recording. I wanted to just go ahead and quickly make a quick note that when you're protecting a carbonyl group, you do need an acid catalyst. That is part of the process. And then to get rid of it, you just use water. And yeah, that's all. Sorry, water with acid. Resume recording. Okay, so we're recording again. First thing I'm going to do is like a drink of water. People are reading fast. That's cool. We've already covered most of this, but basically, Lindlars are going to take double bonds back down to single bonds. And I mean, you guys have talked about that a lot. There's a lot of different ways you can do all of these things. Really, I'm just gonna like talk about some of this, but a lot of these are things you guys have been doing all of Orgo, so hopefully it's just kind of putting it all together for you. You can use, the X represents just any kind of halogen. So like for these, I use radical bromination. You can use anything. This could be a hydrogen, or it could be a carbon. And so you can switch this out for whatever. And basically, to get from here, this alcohol to a halogen, you're going to use PbR3 or SOCl2. And those are going to function very similar. It's just SN2 reactions. We've also got just regular heat and water will add to Markovnikov alcohol, and it'll add it with shifts and that sort of thing. And then to actually like go from a double bond up, that's one of the harder things. So remember when I was talking earlier about using sodium and nitrogen and how you can do different types of stuff with that to basically, oh, I dropped my microphone. Here's the microphone. To add and take away double bonds, you're going to want to use the sodium and the nitrogen with two hydrogens for this. yeah, anyway, sorry. These are, so again, this could be an alcohol, or sorry, an aldehyde or a ketone. Sorry, I've been doing this for like 3 or 4 hours now, so I'm getting tired. This is just like what you guys have been talking about when you do, like at the very beginning where we add 3, we get a triple bond and we take it down and oxidize it all the way down to a ketone or a aldehyde. And so we can also get to this point by doing any kind of alcohol and then adding PCC, because PCC is one of those softer oxidizer. And then from here, there's all sorts of stuff you can do. Actually, when you add just water, water makes diols. And so these diols are super duper unstable. They're actually pretty prominent in like blood chemistry and stuff, but we don't need to talk about all that. But there's a lot of fun stuff you can do with that. Also, this is not useful. There's not a lot you can do, a lot of chemistry you can use with this. So not really something we talk about much. But it's important to know if you just add water, like, it's not going to do a lot. Wittigs are just like what we've been talking about. You replace the oxygen with a carbon. This right here, we literally just did this with in the first part of it, where we're taking away this potassium, it's dissociating. And then basically the cyanide is going to attack here, and that'll punch out this as originally just a charged oxygen. But then we've got the hydrogens also in solution. So like cyanide as an acid form, that's going to keep it protonated. This right here is really just a matter of you do like an alkyne, and you're going to use this. So you're going to use that sodium and I don't know, amine. I guess it's just called an amine. It's weird to see just two. So I don't know what that is called when there's a nitrogen with 2 hydrogens and it's a negative charge, but it doesn't really matter. It's just know that that's going to take off, that to make this into 2 electrons there. And so from there, you've got this right here. That's the product of step 1 and 2 there. And then you'll use your acid workup to just make that into an alcohol. And then, like I've been saying with imines and amines, don't overcomplicate them. Whatever is hydrogen is going to become bonds. And so, yeah, that's what happened here. These hydrogens disappeared and became bonds. And yeah, that's all I'm going to talk about for that first part. Moving down to this, this should be actually really quick because these synthesis problems were a lot easier than they look. Really, you just use PBr for this first alcohol part. And what you're going to notice is this looks kind of scary at first. But if you see it as, I know that this right here is something that I just added as a ketone, it helps a lot. Because then it's just a matter of getting this into a Grignard. So we can use PBr2 or PBr3 to swap that out, and then just drop it into some magnesium and ether solution to make the Grignard. And that Grignard is going to react and attack the electrophilic site on the carbonyl. And then the acid workup will make sure it's an alcohol. And that's all there is for that first one. Are there any questions on that? Cool. Moving down, we've got basically the same thing here, except for you've just got to recognize that, like, when you see this 2 carbons with an alcohol on the end, your mind should automatically think of epoxides, because what epoxides do is something will punch it on this side, and then those electrons fall back this way, and that leaves like a a negative charge that can be quenched, I guess you could say that, by the acid at the end. So that's all there is for the second one. The third one is where we're going to talk about masking. And so masking is important because if you react, for example, like acid with a ketone, it's going to mess with the ketone. This ketone will attack that acid, and it'll make it it'll make things very complicated very quickly, much more complicated than you need them to be, because then you've got a positive charge here with this, and that makes these like an incredibly electrophilic site. And if you want to do chemistry at this site, that pretty much always is going to create the center point for any kind of reaction to be on the ketone. So the reason that we do masking is we want to make sure that we're not touching that part of the particle or the molecule. And that was a wonderful voice crack to say what we're not doing. So yeah, you want to use acid with these. Acid is how you actually, start that reaction. It is still, that's the first part of that reaction, is the formation of this. But yeah, from here you just do magnesium and ether, and that creates your Grignard reaction reagent. And then because you've got this protected, you can add all of these carbon-carbon bonds. So becoming comfortable with seeing these as just something that can be protected and then become like a no factor. And then also seeing that this is all just one molecule. And I feel like I said all really weird there. But that's all one molecule. And all that's happening is that one molecule is reacting with a Grignard. So yeah. And whenever you see something long and you see a lot of carbon stuff, but then you also see a random alcohol in there, your brain should think about Grignards of this reaction right here. Because I mean that is something that's a very common way of making carbon-carbon bonds, and carbon-carbon bonds are stable and they're hard to break, and they're hard to make too. So that's a big emphasis of in organic chemistry and in general. You can do all kinds of decorations, but carbon-carbon bonds are usually pretty concrete. It's a big deal to break those. All right, that's really it for this. Are there any questions about this content?
Can you just go back up to like the flowchart thing so I can get a couple of them down?
For sure. I overshot it here. And this certainly isn't the only way to do it. There's a lot of ways you can do elimination. A lot of ways you can do a lot of these things. Yeah, of course. Glad I could help, Matthew.
Okay, I got it. Thank you so much.
Yeah, of course. Alrighty, I'm going to end the recording here.